Proving the sieve works is actually a total mess. There's a lot of arguments that we haven't seen yet and involve inequalities that may not be super intuitive right out the gate. So anyway, let's get started. The premise of the sieve is that a non-prime number n has a prime factor less than or equal to the square root of n. And that is it. It doesn't get anything greater than the square root of n. And this is the key thing, because if it did, then the sieve algorithm would not work. So let's go ahead and prove that statement. That being, a non-prime number n has a prime factor less than or equal to the square root of n. We can start off by proving that every positive integer has a prime factor. Mind you, this actually is something that we've already proved by showing that every positive integer has a unique prime factorization, but aside from that, we're just going to continue with this just to get us warmed up for when things get a little weird. To do so, we're going to go ahead and use strong induction. Our base case, n equals 2, is trivial, as 2 is prime and is a factor of itself by definition. Because apparently 2 is great for base cases, because that's what all of our base cases thus far have been. I mean, if it works, right? Next, we suppose that this is true for all numbers 2 up to n minus 1, and consider the case of n. If n is prime, we're done. If not, n factors into two numbers a and b, both of which are in the set 2 all the way up to n minus 1. So a and b have prime factors by the strong induction hypothesis. So n must also have a prime factor, and we're done with the easy part. Now this is the point where things can get a little bit tricky if you're not keeping track of all of the mathematical modifiers that are floating around with our numbers. So here we go. Let n be some positive whole number and let p be the smallest prime factor of n. We're going to argue by contradiction and suppose that p is greater than the square root of n. If p were greater than the square root of n, then there would be a prime factor that was greater than the square root of n, not less than or equal to it. And so the sieve wouldn't pick up this prime p when we were searching through for them. So n is the product of p and some number q. Remember, again, we are assuming n is greater than 2, and it's not prime, so q is not 1. N, mind you, is also the square root of n times the square root of n. Since p, by supposition, is greater than the square root of n, q must also be less than the square root of n. And since it is not 1, q also has a prime factor, and we'll call it k. This implies that we have the following inequality chain. But since k is a factor of q and q is a factor of n, we also know that k is a factor of n that is less than p, which is the contradiction. So the supposition that p is greater than the square root of n is false, and we end up with a proof of the premise that the sieve of Eratosthenes is built on. Anyhow, that's all I have for you today. Apparently June is becoming the month where I just try all the new things all at once. So if you enjoyed this video, let me know and give it a thumbs up, and I will continue making videos in this format. Otherwise, if you want to go ahead and go back to the beginning and start and learn some other things about primes or take the other route, you can go up here. If you want to see me do other math stuff, you can hang out down here. And if you want to subscribe to my channel and watch more mathematics stuff as it comes out, you can find that over here. Anyhow, I am Nathan, this is Chalk, and I will see you next time.